To start out with, before we get started today, I want to show you something quick on Canvas that I've figured out how to set up that may be helpful to you at some point. So I figured out how to set up appointments on Canvas. I've set them up for the month of October for the mornings that I'm available when I don't have meetings, and for our office hours now that we don't have to see tribes every single day. Mondays and Thursdays will be office hour days. So I've set that up on Canvas, and you can access that if you need to see me at some point. So I just want to show you quick how to do that. It's pretty easy. So if I go in here for a second and make this look like what you will see. Maybe. Come on. There we go. All right. So student view is going to look like this. So basically what you need to do is go up to your calendar up here. And then right here, you have choices about how you want to set up your calendar, whether you want to see it by the week, see it by the month, see it in agenda form. And then you have this fourth choice of scheduler. If you click on scheduler, you have this entry that says October meeting times. So I've just set it up for the month of October for the moment. My goal is that at the beginning of every month, I'll have it set up for the next month, so this will always be available to you. But off to the side here, where it's kind of an orange box, it says you can sign up for this. So if you click on that, it will show you where open times are. So I've taken the 7:45 to 8:30 time in the morning and split that up into 3 15-minute sections. And then we've got the office hours times on Mondays and Thursdays. That's another 15-minute section. So I've set them up as 15-minute sections for right now. In most cases, that's probably enough. But if you, for some reason, feel it's not, like you need to see me for half an hour, you can sign up for 2 different times. There's no limit to how many times you can sign up for. And so if you click on one of these boxes that represent a meeting time, you'll get a box that looks like this. So it tells you exactly what date you're talking about, October 9th from 8 to 8:15 or whatever it is. And then down here, as long as it says slots available 1, that means it's an open time. There's 1 slot available there, 1 person can come in during that time. If you notice, and to come in you just hit reserve, right? You might notice here that it looks like the boxes over here are a little bit grayish. That's because I've had some students who've already signed up for times for tomorrow morning already. So when it looks kind of gray, it means that time's already been taken. If you're not sure, because it's not real obvious, when you click on one, it's going to say slots available none, because somebody's already signed up for that time. Okay, and you don't have that reserve button to use. You'll also notice that over here on the little calendar, you have all these days that are kind of highlighted with blue bold print. Those are all days that have an appointment time available in them. So you could also come over here and go, well, I know I want to meet with her next week on Tuesday, so I can just click on that and it'll pop right to next week, and then you can pick your time. As soon as you click reserve on this, I get an email that tells me you've signed up for this time as an appointment time, so I'll know you're coming in and I can plan accordingly. Okay, so you don't necessarily have to come and tell me, you don't have to email me, just do it through this. I'll know you're coming in, and then you can come in and ask questions or look at tests or whatever you need to do. Okay, so it's all about getting to your calendar and then clicking on that scheduler choice. Okay, any questions about that? Does that make sense? Okay, so then the other thing is, I realized this weekend as I was kind of wrapping things up for class today that I never got the answers to our 2-1B practice up online. So I did that this morning. So go ahead and get on Canvas really quick and take a minute and check over those answers. They are there now. So just download them. 2-1B right there. Click on that, the answers are there, check them over quick, and then I'll give you a chance to ask some questions if you need to before we get started on our lesson today. Any questions from that homework? Which one?
The challenge.
The challenge? Okay. All right, so in the challenge, we are shown that we have a mountain over here. And we are driving toward the mountain. And it says at one point we stop and we look, and the angle of elevation from where we are to the top is 3.5 degrees, right? And then we drive for 13 miles, and we look again. Okay. What happened? There we go. All right, 13 miles right here. And we look again, and now the angle of elevation right here is 9 degrees. And the question is, how high is the mountain? Okay. Now, the idea here is to try to use right triangle trigonometry as a way to figure this out. And the reason it's a bit of a challenge is because at least I haven't figured out a real direct way to do this. You have to do it a little bit indirectly. So you have to consider two different right triangles. You have to consider this one like that, and then you have to consider the smaller one like that. Okay? So in the purple one, I have this angle. I want to know the opposite side, and I have at least some information of the other leg, the adjacent side. I don't have all of it though. I only have this 13 miles right here, and so I just labeled this with X. I don't know how much it is right now, but it's the same in both triangles, right? So now I can say that opposite over adjacent is tangent, so taking the tangent of 3.5 degrees has to be equal to h over this entire side, which is now 13 plus x. Now by itself, that's not real helpful because there's two different variables. But if I also set up the second triangle using tangent of the 9 degrees, then the tangent's going to have to equal what? H over x. So now that I have two equations with two variables in them, I should be able to solve them. And the idea is the h represents the same thing in both, the x represents the same thing in both. So if I can get this to equal h by multiplying both sides by 13 plus x, and then get this to equal h by multiplying both sides by x, then I can replace that in for that h and set up an equation with just the one equation, the one variable in it.
Sorry, please.
So if we go tangent 3.5 degrees times 13 plus x is supposed to be equal to h, but h is also equal to tangent of 9 times x. Now I have one equation with just the x in it, and I solve for x. Now at this point, I probably have to actually go ahead and figure out what tangent of 3.5 is and tangent of 9 is, and work with some decimals that go out a few places, so it's fairly accurate. But this allows me to write one equation with just one variable in it to solve for that. Now, what I have to be careful about is when I solve for that, what I'm solving for is this, not this.
Wait,
Okay? So once I solve for that x,
okay.
I still have to then go back to one of these and put it in to figure out what the h should be. Okay? Because what I solved for was this part, not that part. So I still have to go back and solve that last part. Now there may be another way to do that, but that's the way that made sense to me. So that's why I labeled it as a challenge. If you didn't get that one, don't panic. Don't think that problems like that are going to be on the test. But if you really understand how to use the right triangle trigonometry, you should be able to at least get part of this kind of figured out and know that where are the right triangles I'm trying to use and how could I set things up and try to go from there. Okay, anybody else? Questions off the applications? All right, and let's get started with our next lesson. So our next lesson is another one that we're actually going to spend a couple days with. It's on angles and their measures, which maybe sounds really simplistic, right? That's what my title page done. But it's amazing, I think, how much understanding what we're going to talk about in terms of angles and all different kinds of things about angles is going to make the actual trig easier. I think in the past when I've had students that have struggled with the trig, a lot of times it's been because they weren't really comfortable and familiar yet with the angles they were using with the trig. And so based on that observation, I want to make sure we've really got a good solid handle on our angles and everything we need to know about those angles before we go on to the trig part with them. So we're actually going to take today and Wednesday in this particular lesson. So when you look on Canvas, you'll see 2.2a and then 2.2b will be on Wednesday. And I think what you're going to find today, the disclaimer for today, is you're going to find that things are unfamiliar. I don't think you're going to find that things are difficult. If you're struggling at all through today's lesson, it's just because you're not familiar with it yet. So hang with it, try to do the problems I asked you to do, make sure you're doing the practice because the familiarity is what's going to make it easier. Okay? All right, so what we're talking about here today is trying to take trigonometry beyond just right triangles. Okay? What we were doing before break, as long ago as that feels, is doing trigonometry based on the ratios of sides on a right triangle, which is all fine and good. It is definitely part of what trigonometry is about, but it limits us because when we talk about finding the trig functions, we're always talking about either this angle or this angle, right? We're never being asked to find a trig function for that angle. That's the right angle. So it's usually one of these two that we're asked to find the sine or the cosine or the tangent or whatever for. But what kinds of angles do those always have to be? Acute angles, right? If this is a 90-degree angle and three angles in a triangle have to add up to 180, these two have to add up to the other 90, which means any one of them by themselves always has to be less than 90. So when we're talking about right triangle trigonometry, we're limited to just working with acute angles. So we can get really good at finding sine and cosine and tangent of things that are acute, but what happens when we move beyond that? Trigonometry is not limited to just acute angles, and we have to know what's going on when we talk about obtuse angles, or when we talk about a 250-degree angle, or a negative 17-degree angle, or whatever that all means. So that's kind of what today is about. It's taking that next step into trigonometry that takes us beyond just the right triangle trigonometry that you saw in geometry class. Okay? So, instead of thinking about angles in terms of being made by the sides of a triangle, we now want to start thinking about angles in terms of rotation. Okay? We're going to take rays, right? Angles are always made up of rays that meet at an end point that we call the vertex. We're going to take a ray. We're going to rotate the ray around the circle to create an angle. That's what's going to allow us to get beyond 90 degrees and to get to other kinds of angles. Okay? So we want to now start thinking about angles in terms of circles rather than just in terms of triangles. Okay? So, a little bit of vocabulary. First, I'm going to put something up here that looks a lot like the circle protractors that are in your baskets. So if you want to get one of those out so you can kind of play with it as we do some stuff here, go ahead and take it out of its sleeve, and I'll try to get mine up here on the board. Whoop. That's not what I want. Okay. So if you think about angles in terms of rotation instead of in terms of being created in a triangle, there's some vocabulary that goes along with that. And the first has to do with the sides themselves that make up your angle. We have an initial side and we have a terminal side. And what they mean is what you expect them to mean. Initial means what?
And what you have in the first place.
Yeah, so where we start, right? What we have in the first place. Terminal would mean where it stops, where we end. So that's exactly what these are. An initial side is the side, oh, let me change the color of that. Keep things consistent here. So the initial side is the side where your rotation is going to start. And then as you rotate through, wherever your other side ends up is called your terminal side. Simple enough. So right now, if you look at the circle with the protractor that I have on here, my initial side is this green line right here that's lined up with the 0 on the outside scale. So we're going to use the outside scale here. It's lined up with 0. Okay, you can do the same on yours. You'll actually notice that the red line is lined up with 0 to the right. And I think that's the outside scale on yours too, right? 0, yep, that's the outside scale. That red line corresponds with this green line that you're seeing up here. Okay, so if you move your protractor so that the part that moves actually lines up with that, that would be your initial side. And then, as I take this green line, whoop, gotta keep remembering to. And start rotating it, this line stayed put. My initial side kept a ray there. And then as I rotated it, where my other side ended up becomes my terminal side. And then how much that rotated through, that's the angle that I've created. So in this case, I've created a 111-degree angle. Okay, but it's as a result of rotating rather than a result of making a triangle. That make sense? Okay. As I rotate, I can rotate anywhere. So here's where the ability to have an acute angle, if I stay in here, get my shadow out of the way, right? In here, I'm less than 90. But I can go to 90, I can go past 90, I can be over here in obtuse land, I can come out here to 180 for a straight line, I can go beyond that, I can keep rotating, I can keep rotating around over and over again. Now my protractor is limited by the fact that once I get to 360, it starts over again. But technically, if I'm going around and coming back, let's say I go right about there. This is really a 400-degree angle that I just created, because I went all the way around once for 360 degrees and then went an additional 40 beyond that. So this would be an example of like a 400-degree angle. So we can get kind of freaky with these. Like, we can talk about all kinds of angles. And they can get really big depending on how many times we want to keep spinning around the circle. Okay? When we are doing angles like this, we generally want to start out in what we call standard form. And standard form simply means that, come on, there you go. Ooh, that was bad. Try that again. There we go. Standard form means the initial side of your angle is always going to be on the positive x-axis. So what we mean by that is when you look at like the circles that I gave you on the little worksheets that I handed out, or the circle that was up here initially before I put the protractor up, that circle has a horizontal line that cut it in half. It has a vertical line that cut it in half. And when you look at that horizontal and vertical line, they start to look like x and y axes from graphs. The origin of the axes is the center of your circle. It's where the vertex of your angle is going to be, because that's where the rotation happens. So if you think about those lines as x and y axes, then the positive x-axis is where our initial side always starts when we talk about being in standard form. And you rotate from there. Okay? Now, we can create angles that are positive. We can also create angles that are negative. Which one they are depends on which direction you rotate. So a positive angle is when you rotate counterclockwise. So as I was showing you a few minutes ago, if I am rotating counterclockwise, opposite of the clock, I am creating a positive angle. So that's a positive 283-degree angle right there, because I started here and went this way around the circle. Okay? But if I want a negative angle, then I just have to go clockwise. So if I start over here, so if I start back here at 0, 0, but this time I go this way. Oh, come on, there we go. Now again, there are limitations to my protractor. So my protractor says I'm at a positive 328-degree angle. Well, that would be true if I had gone this way around. But I didn't. I went this way. And so having gone clockwise rather than counterclockwise, what I really created here was a negative, what would that be? 35? So I've really created a negative 35-degree angle because of the direction that I went to create it. I went 35 degrees in rotation, but I went in a clockwise direction. That makes it a negative 35-degree angle. Okay? Now, that also brings us to this last idea in our vocabulary list, which is the idea of coterminal angles. Just from the word, what does coterminal suggest? Yeah, exactly. So the terminal side of your angle ends up in the same place. You have more than one angle where the terminal side ends up in the same place. So in this case, the positive 325 angle that I could have created by going counterclockwise, and the negative 35-degree angle that I created by going counterclockwise, those two angles are coterminal because they both have this as their terminal side. Right? So positive 325 and negative 35 would be considered coterminal. We don't really need our computers right now, so if you shut those, I would pay attention. Okay? Now, are those the only two coterminal angles I could come up with for that terminal side? Anybody come up with another one?
Wait, this is good.
Mm-hmm.
I get the 325, but I'm still kind of confused with the negative 35. Like, I know you went clockwise.
Yep.
But how'd you get 35?
Because right there is 33, and right there is 34, and that's 35.
Right, thank you. Sorry.
It's also because if this direction went 325 degrees,
Yeah,
then how much did I not go? 35, because all the way around is, right. So you can also figure it out that way,
Yeah, okay.
by subtracting. But it's a negative 35 because of the direction.
Yeah, okay.
Yeah.
Thank you.
So back to my question, are these the only two coterminal angles I could have for that terminal side, or are there others? And if you think there's others, give me an example. So if I say it's a 325-degree angle, does that indicate that I went around several times? No. Could I go around several times and end up in that same spot? Yes. So what would be another possible coterminal angle if we follow that logic? What if I didn't stop here the first time around? What if instead I happen to stop there the second time around? Then actually, what angle is that? Six what? Not quite. How many more degrees did I go around if I stopped there the second time? 360. So take the 325, but add another 360 because I went all the way around first before I went to 325. What kind of angle do I have? 685. Oh, why that's being so such a thing. Sorry. So weird. Come back. There it is. Okay, so the moral of the story is when we talk about coterminal angles, there are lots and lots and lots and lots of different possibilities that are all correct because we can keep rotating as many times as we want to, both positively and negatively. When we see a problem like this in the homework, generally we want to not get too crazy about it because it just takes more work. But don't think that, oh, well, there's just one angle that goes the positive way and one angle that goes the negative way, and there's only those two possibilities that could be coterminal. Because we're not limited to just one rotation around the circle to end up in the same spot. I can go 5 times around the circle if I want to. It's a really ridiculously big number of degrees that I would go, but I could, and it would be coterminal just like these were. As long as my terminal side ended at that same spot. Okay? Alright, so what I would like you to do is to take a minute on the worksheets that I handed out to the tables. If you don't have one individually yet, get one. On those worksheets, I want you to take a minute and I just want you to sketch how big the angle should be based on this idea of rotation for the top 4 circles. So the top one is going to be a 30-degree circle. Top right, draw what you think a 120-degree angle would look like. Did I say circle? Sorry, 30-degree angle, 120-degree angle, a negative 45-degree angle for this one, and then a 210-degree angle for that one. Sketch it as best you can, but draw what you think that angle of that measurement would look like in a rotational setup like this.
Is there only 4 or is there only 2?
At the moment, there's only 4. Michaela, come show us what 30 would look like. Okay, everybody agree with that? Okay. I did, as I was walking around, notice a couple of you shading in the inside of the angle once you have drawn it. Don't do that. It's kind of a picky thing, but we are at some point going to talk about area inside of the circle that's made by our angle. And so if you're shading it, it's starting to look like you're talking about the area, not just how much rotation there was. So don't do the shading unless you really are talking about area. I think probably why some of you were doing that was to show sort of which way you were rotating. So the better way to show it is just to give yourself a little arc with an arrow to show that that's the way I rotated around to get there. Okay, makes sense? And again, standard form, so we're always going to start here with our initial side on the positive x-axis and then rotate from there however far we need to go. Okay? 120. Emily, want to do 120 for us? Sometimes hard to line up with the right line, isn't it? Okay? Everybody agree with that? And which way did you rotate? This way? So again, positive 120 means rotating counterclockwise, but this time notice we went beyond that 90-degree mark. We're over here a little bit farther now into something that's more obtuse. Okay? How about, this down a bit. Negative 45 degrees. Alfred? Negative 45? Think about which way and how far. Try instead of like this, a little more angled. Sometimes that works better than straight up like that. Where do you want to put your terminal sign?
It's right here.
I'm asking you. Maybe press just a little bit. There we go. Okay, and which direction did you go to get there?
Like.
Okay, good. So this time we've got to go this direction because of it being a negative 45 degrees. Okay, last one, 210. Nicole, come show us 210. Just kind of make sure it's pressed a little bit when you do it. There you go.
Here.
Okay.
So it's like 190 then. Yeah, that's there.
Okay, so when we draw our angles, do we want to do this part?
Oh no.
No, we don't want to draw that part.
Yeah.
Okay? You can be thinking that part. You can be thinking this is where I'm rotating,
Yeah, we don't.
but we don't want to draw that part. So in terms of what you want to end up with on your paper, kind of do like that. Now, having said that, it's good to do this little one to show which direction that you went. But to do the big one around the outside kind of starts, again, making it look more like area of a section rather than just the angle itself. Okay, everybody good with that? Kind of have an idea of what different sizes are going to look like and where they are in the circle? All right, so now just for this one, just for the 210 that we just finished, I want you to give me one positive and one negative co-terminal angle to 210. So come up with one other positive angle and one negative angle that would be co-terminal to our 210. Let's write it off to the side.
Just one pair.
Just one positive and one negative. All right, somebody got a positive one? What's another positive angle that would be co-terminal to 210? How much? 570? How did you get 570? Whoops. So we take the 210 degree that we're given, and then we add to it another rotation. Right? So instead of just going around this much, we're going to go all the way around and then go back that much. So we're going to go 210 plus another 360 because we're just going to add one more rotation to our angle. And so that's going to give us our 570 degrees as a positive angle. What about negative? Somebody give me a negative coterminal angle.
Would it be 150?
Why?
Because 360 is 720. So like 720 minus 570. Would that give you negative one?
Okay, you actually don't have to go quite that far out, that many rotations. You can just go in terms of one rotation, right? One full circle around. If I've already gone 210 of those degrees,
Oh, okay.
then how many degrees have I not gone?
150.
The 150, right? So actually you can take kind of the same idea, take your 210, but then subtract the 360 from it. And not only will that tell you how much of the circle you haven't rotated through yet, it'll also end up giving you a negative answer because you're taking the smaller minus the bigger. So we end up with a negative 150 degrees as a negative coefficient. So that means we started here and went this way to get to that terminal side. Okay, makes sense? Because you're going to be doing that in homework, so everybody clear on that? Okay, so when we're measuring angles, there's two ways that we can actually measure them. We can measure angles in terms of how many degrees of rotation they've gone through, or we can measure them in terms of how many radians of rotation they've gone through. Degrees are probably more familiar to us at this point, which is kind of why I started with those at the beginning of this lesson. But degrees are not always the most useful. And part of the reason is because if I'm talking about a measure in degrees, I have to keep the degree label on that measurement. And so as I'm working with that measurement in the context of a problem, it sometimes gets in the way. It gets really messy trying to deal with that degree label. One of the really nice things about radians is that I don't end up with a label. And we'll see why here in just a second when we talk about the definition of what a radian is. So when you start talking about angle measures that you need in a physics class or something like that where you're measuring certain angles because you're talking about force or you're talking about all kinds of different things, rotational phenomenon, whatever. If you talk about degrees, things get messy. You talk about it in terms of radians. Because there is no label, you don't have to try to keep track of the label in the answer. And so the work becomes much easier. Okay? So, with the degrees, just to kind of, again, reiterate what we know, how many degrees is a whole circle all the way around? 360. If I only want to go halfway around, then it's how many degrees? 180. And then the positive vertical axis would be how much? 90. And the bottom negative vertical axis would be? Could be negative 90. How about as a positive? 270. Good. So in terms of degrees, those are kind of the benchmarks. Everything from 0 up to the 90 is acute and is in this quadrant. So again, we can kind of go back and forth between this idea of circles and the idea of graphing with x and y axes. With the thought of these being x and y axes, that means we have quadrants. And so 0 to 90 is going to make up our first quadrant. Then this quadrant from 90 to 180 makes up our second quadrant. And then from 180 to 270, we have our third quadrant. And from 270 to 360, we have our fourth quadrant. And this starts to explain why our quadrants are numbered the way they are. Do you ever get taught this in Algebra 1 and go, why does the numbers go that way around? Like most of the rotational stuff we're used to is clock stuff, so it's like, it should be going this way around. Why are the numbers going this way around? This is why. Because when we talk about making angles in rotational situations, that rotates counterclockwise. So we number the quadrants in the order that we rotate through. Okay? So the 90, the 180, the 270, the 360, those are kind of those benchmarks that move us from one quadrant into another when we're talking about degrees. Now, when we're talking about radians, the definition of a radian is this. Come on. Really? There we go. Okay. So 1 radian as an angle is the angle that's needed so that the arc that you've cut off on your circle is equal in length to the radius of the circle. Okay, that's the actual definition of what a radian is. Now, let me try to show you what that actually means in case that seems a little bit like gobbledygook. So, on my picture here, let's use this outside circle. Okay? Which means that my outside circle Oh, I don't have quite enough for that, so we're going to use this next one. Let me draw that one so we know what we're doing. Okay, so we're going to use this circle right here. Okay? So the radius of this circle is right there. Okay? Everybody agree with that? Now, if I take that length and I start here where my initial side would start, and I follow along the circle for that same distance, that piece of the circle is called an arc. So the angle that's necessary, starting here on my initial side, the angle that's necessary to make this radius equal that arc, that angle is what we call 1 radian large. Does that make sense? It doesn't matter how big the circle is. So if I decide to go with this circle instead, whoops, I want that to be a different color. Try again. Green. Okay, we're going with this circle instead. If my radius changes to that, let's together a little bit, then how much I go around the circle also changes, but where I end up for my terminal side doesn't. I still end up right there for my terminal side. So because both the radius and the arc are changing at the same proportion, the actual angle that it takes for this to happen stays the same. So it doesn't matter how big our circle is for this definition to work. The angle that's actually created is still the same size, and it's 1 radian long. Now, if we start then going, okay, so if this was 1 radian, go back out here to purple, then add another one, right? That's about where 2 radians is. About there. Add another one, we're out here to about 3 radians. And then we go just a little bit beyond that. Keep going. A little bit beyond that gives me halfway. But if I want to go all the way around, keep going. Right about there's 4 radians. Right about there's 5 radians. Right about there is going to be 6, and then I've got a bit more. So the question then is, what do we use to represent how many radians are in a whole circle? Or maybe it's easier to think about how many radians are in a half circle first. So halfway around we had 1, 2, 3, and just a little bit more. Do you know of any number we use quite often that is equivalent to something just a little bit bigger than 3? All right, let's take a different approach. Let's say that whatever our radius is here, which is what creates this distance, which is what creates the 1 radian, let's just say it's 1 unit. Doesn't really matter if it's centimeters or inches or feet or whatever. It's 1 unit. How would I find the circumference all the way around that purple circle? Oh, geometry. Dang, that was a long time ago. How do you find the circumference around a circle? What's the formula
Higher square.
for circumference? If I'm squaring stuff, that sounds like area. 2r pi, or 2 pi r. But in this case, what's my r? What? What did I say I was labeling my radius as? 1 unit. So that means circumference all the way around is let's make that orange. Come on. So all the way around the circle is 2 pi radians. If I put the 1 in here for my radius, what I'm getting is the distance all the way around. And whatever my circle is, if we just say the radius of that is a 1, then the distance all the way around the circle is always 2 pi. So in terms of radian measures, all the way around the circle is always 2 pi. Well, what decimal is approximately equal to 2 pi? 6.28. 1, 2, 3, 4, 5, 6, and a little bit more. 6.28. So what then is halfway around the circle? How many radians would that be? Approximately. I want something more exact. Halfway around the circle is pi, right? If all the way is 2 pi, halfway is going to be 1 pi. What is my vertical axis going to be? Sorry? How many radians would my vertical axis be if I went from here to there? Whole circle is 2 pi. Half circle is pi. Pi over 2, right? Because this is going to be halfway of the half circle, right? So pi is halfway around, and my vertical axis would be half of that, so pi over 2. Okay, here comes the tricky one. What's the negative axis? Negative axis is halfway between what and what? This is pi. If I get all the way back around here, I'm at 2 pi. So what's halfway between those? One and a half pi, which we write as 3 pi over 2. So this one is pi over 2, and this one is going to be 3 pi over 2. Okay, so as you can see, when we talk about radians, a lot of times, not always, but a lot of times, the kinds of numbers we're dealing with are numbers that have pi's in them. And that's kind of a tip off that, yeah, okay, I'm dealing with radians, not degrees. But it's not always the case. So if I ask you to show me an angle that has a measure of 5, how do you know whether I'm asking you for 5 degrees or 5 radians? Yes, exactly. 5 degrees has to have the degree sign behind it, which means that anytime you are writing an answer that is meant to be a degree answer, you must include the degree sign. Because if you don't, if you just say 5 with no label behind it, what you really mean is radians. And they are completely different. 5 as degrees. Is going to be something maybe about right here. That right there is 5 degrees. 5 as a radian is 1, 2, 3, 4, 5. That was the one we came up with like way down here. All the way around. That's 5 radians. That's totally different than 5 degrees. So you have to make sure that you are distinguishing which one you're talking about by either using the degree sign when it is degrees or not using any label when it's radians. If you want to be sure, you can write RAD as a label, but it's not necessary. The reason it's not necessary is because when we come up with what this measurement is supposed to be for the angle, we are taking the ratio of this length to this length. Which means if this is in centimeters, then this is in centimeters, and the centimeters cancel out. Right? If I'm taking the ratio of those two things, and they're supposed to be the same, whatever their labels are, whatever their units of measure are, cancel out. That's why radians have no labels to them. There are no units to radians, which is why you use those in physics problems more than you do degrees. Okay, so last but not least, I want you to take a minute. Actually, this is not quite last but not least, but it's close. I want you to take a minute. I want you to write these 6 radian measures on the side of your paper. And beside each one, I want you to write down which quadrant you think the terminal side of that angle would be in. You don't necessarily have to draw them, but you've got the circle there that you can use as a reference. Okay? But write down the 6 different angle measures in radians, and then beside each one, just write down 1, 2, 3, or 4 as to which quadrant you think the terminal side of that angle would be in. Sorry? How you would rotate through them. Now that we know how to rotate, it's just the order you would rotate through them. Okay, I know that's not a lot of time to work through them, but I want to make sure we do all understand where these would end up. And then there's one more thing we need to get to before we run out of time. So let's go ahead and work through them a little bit together. So, pi over 3. Lift up how many fingers? 1, 2, 3, or 4. Where does it go? Which quadrant is the terminal side for pi over 3 going to end up in? 1, 2, 3, or 4. Lift them up. Come on. Take a guess. Okay, good guesses. Come on, you know this. Be confident. It's in 1. Which of these lines is actually the pi over 3 line? First, second, third, or not one of the lines? First, second, third, or not one of the lines? Which one's pi over 3? This one? Think about what you're saying. Pi over 3. Pi, the top half, is being divided into 3 sections. Right? So how much looks like 1/3 of the top half? This one? That one? That looks like 1/3. This looks like 1/3 of the top. 1, 2, 3. Nope, I didn't even get close. 1, 2, 3. Nope, still not there. The third one. This right here is 1/3 of the whole top. The whole top is pi. I'm dividing it into 3. Right? That's what this is saying. So it's like saying if this is the angle that I went through, I need 3 of those along the top. So there's another one. Right there. Oh, that was really bad. Try that again. And then another one right there. So that makes this pi over 3. That makes this what? I'm rotating through. There's pi over 3. How far am I getting to there? 2 pi over 3, right? 1 pi over 3, 2 pi over 3. One pi over 3, 2 pi over 3, 3 pi over 3. What does that reduce to? Pi. Okay, so I'm halfway around. Keep going. What's that one going to be? Come on, folks, follow the pattern. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. What's that one going to be? 5 pi over 3. Now you're catching on. What's that one going to be?
6 pi over 3.
Which reduces to? Bingo. Okay? Now, let's go away from this list for just a second, and let's do that with the other lines. So how would you say this line is related to the blue lines? Like, what does it look like this line is compared to that one and that one?
It's half.
About halfway, right? So if this is pi over 3, what would halfway be? From here to here is pi over 3, so what would from here to here be? pi over 6. Good. Okay, so this one is pi over 6. So there's 1 pi over 6. There's 2 pi over 6. What does that reduce to? Pi over 3. Got it. How many? 1, 2, 3 pi over 6, which reduces to pi over 2. Got it. Next. 4 pi over 6 reduces to 2 pi over 3. Got it. Next. 5 pi over 6. I don't have that one yet. I'm going to try to do better and draw that in. Okay. Next. 6 pi over 6, which is pi. Got it. Next. 7 pi over 6. I don't got it. I'm going to label it. 7 pi over 6. Next. Which reduces to? Got it. Next. 1, 2, 3, 4, 5, 6, 7, 8, 9 pi over 6, which reduces to 3 pi over 2. 10 pi over 6, which reduces to 5 pi over 3. 11 pi over 6 is that one. Go ahead and draw these in since they're just axes. Okay, so now all we got left is this one. Let's make that one equal. So how do you think this line compares to the other stuff we have labeled? What's it look like to you? That one right there. Half of what? Half of pi over 6? Half of pi over 6 would be down here. So if I take this blue, you told me half of was this one. That doesn't seem like they're the same. But you're on the right track. What is this half of? It's half of 1/4? It is 1/4 because it's half of pi over 2, right? So this quadrant that goes up to pi over 2, this purple one looks like it's right down the middle of it. So if all the way up to this axis is pi over 2, then what is it up to that purple line? Pi over 4. Okay, so same thing. There's 1 pi over 4, which is 3 pi over 4. Okay? It's my next rotation. 4 pi over 4, which is pi. Next. 5 pi over 4. Next. 6 pi over 4, which is 3 pi over 2. Next. Oops, I got off the line there, but you get the idea. And then finally, 8 pi over 4, which gets us back to 2 pi. Those tiny itty bitty things that are on your graph, that's what they're saying. But they're really hard to read. So if you want to label one of these for your own reference with this, what's nice about this with the radians is that when you start looking at these actual special angles for radians, there's patterns all over the place. Look at the patterns of those denominators. We're going to start using those patterns in our future lessons to help us know where things are, know what quadrant we're in, know what trig function we should get, on and on and on. So start looking at them now. Start getting familiar with them now. Okay? So if we keep going now, we had our pi over 3 being in the first quadrant. Where's 3 pi over 4? Put up a finger, or number of fingers, 1, 2, 3, or 4. 3 pi over 4, which quadrant did you say it was in? Okay, should be in 2, right there. 3 pi over 4. How about a negative pi over 6? How many fingers? On that one, negative pi over 6. And I caught a few of you. Which direction are we going? Clockwise. So from initial, we go down. How far? How far are we going clockwise? Pi over 6, right? Is that to the green, the purple, or the blue? The green. The greens were the pi over 6s. So even though in the positive direction we labeled that as an 11 pi over 6, it's still a sixth. So when I go the other direction, I can still use the greens to count. That's a negative 1 pi over 6. Okay, it's just the different direction. How about 7 pi over 3? Hold up your fingers for that one. I don't think that one's going to end up. What should we be counting? The greens, the purples, or the blues? The blues. Now keep in mind, when you count greens, you have to count blues with them. Okay? Because the thirds are just reduced versions of sixths. But these are thirds. We're going to count the blues. Alright, so start here. There's 1. There's 2. There's 3. There's 4. There's 5. How many are we up to? 6. How many do we need? 7. So I keep going. Which quadrant do I end up in? 1. Because I had to go all the way around and then a little bit more to get to 7 pi over 3. Negative 5 pi over 4. Should I count the greens, the blues, or the purples? Purples. And which direction am I going to go?
No, clockwise.
Clockwise, because it's negative 5 pi over 4. So there's 1, 2, right? I have to count the 2's because they're just reduced 4's. 3, 4, 5. So it's coterminal with 3 pi over 4. That would be in the second quadrant. Okay, got the idea? Oh, really? Okay, there's one thing we didn't do, and that's conversions. Okay, being able to change back and forth between degrees and radians. You can probably look it up online. I will try to post a video to help you out if you want to look at that. Or if you just know it, that's great. But you do need to figure it out before next class. So either look it up online or look at the video that I'll give you for a little extra help and figure out those last few problems. Okay? And we will continue with this on Wednesday. So make sure that 2-2A is done by Wednesday.
Yeah.
But I have you.
Yeah, sure, Lauren, here.